Okay, I'll share my screen now. Are these slides visible? Okay. So yesterday we were talking about four different learning paradigms. Can anyone list out four learning paradigms are? Four types. You can type it in chat. Four different types of learning paradigms in machine learning. Yes, supervised, unsupervised, semi-supervised, and reinforcement learning. Yes, that's correct. And yesterday we started with the regression case in supervised learning. Today we'll be talking about classification in machine learning. In specific, we'll be talking about two models. One is logistic regression, and the other one is k nearest neighbors, KNN in short. Okay. So just a small recap. Classification, it comes under supervised learning. The training data, you have a set of feature values. It can be numeric, like age, height, or it can be categorical. Categorical means it can be discrete. Uh, let's say which section you belong to in a class, or the pin code, or which city you live in. Those are all categorical features. And the output value should also be categorical. I mean the label. The label can be whether you have heart disease or not, whether an earthquake will happen or not. So these are all categorical output values. And the model is the method or function that maps these feature values to labels. Okay. And whenever we get new feature values, you use the model to predict the label value. So this is what we do in general for classification. This is an example where the features can be your age, the gender, and income. Okay. You have three features. Using these three features, you can predict whether a person will be a buyer or not a buyer of any specific item. Okay. So yeah, moving on to supervised learning, this is more in terms of the mathematical formulation. You have all these tuples containing the feature values and the output label. You always have these in pairs, the supervised learning scenario. And you deem it as classification only when Y is categorical. Okay. And yeah, again, we saw this example yesterday where each data point is associated with a label, and some more examples. So one is credit card fraud detection. Okay. The features can be user, your location, and your age, and the labels can be whether the transaction is fraud or the transaction is okay. Okay. Only two labels. In the case of, let's say, medical diagnosis for heart disease, okay, what all features can we take into account? What all features we can take to predict, heart disease? You have to remember that the features should be relevant to the output label. Okay. Any guesses? What can be the features? Just name anything. What all features do you think will be relevant? Yes, blood pressure. Yeah, diet, what all you ate, glucose level. Yes, that's good. And so the labels obviously will be whether you have heart disease or not. Okay? This is the binary. We term this as binary classification. Okay, it's either presence or absence of something. Okay, and in the same case for email spam detection, what all can you take into account as features? You can take into account specific the presence or absence of specific keywords, and you can take in word counts, and the labels will be whether the email is spam or it's actually relevant to us. Okay? So these are other examples of classification. And classification, moving on to algorithms that we can make use for classification. The problem statement is somewhat similar to the regression case, but the output value is non-numerical. It's not continuous like height or age. Okay, it's either presence or absence of something. Okay, so we have to use completely different approaches for the classification case. Okay, so these are some of the algorithms we'll be looking at for doing classification, and we will start with k nearest neighbors. Okay, how can we do classification with k? So this is more of a mathematical formulation. You have any two data items in your data set, I1 and I2, and from their feature values, we have to compute something called the distance between these two data points. A very short example, let's say the features can be gender, profession, age, income, and the postal code of where you live. Okay. For person one, okay, these are my features. He's a male. He's teaching. His age is 47. He's earning 25,000 per month, and this is his postal code. Okay? Then there is person two. Okay, and somehow we have to calculate this distance between person one and person two. How these two are closely related to each other. Okay, so you can think of this as similarity. Okay, and of course, all of these uh, features should have a label. So a specific person having these five features will be a buyer, and another person who's having these features will not be a buyer. Let's say a TV. Okay, so this will become part of your training data, and let's say a person three comes into picture having these features. Okay, what do we do, or where do we assign this point? Based on these features alone, can I say she will buy a TV or not? Okay, question three. So this is what KNN deals with in general. You have labeled data with you, these two. You have an unlabeled instance coming to you. How do we predict whether they'll buy a TV or not? And I will explain in the later slides. Okay? And what we do in general is we assign it the most frequent label. Okay? Let's take the city temperatures example here. Okay, cities in India and Germany. Features can be your longitude and latitude. Okay? And the distance I was talking about in previous slides is something called the Euclidean distance. Okay, and this is how you calculate it. This is the mathematical formula here. Okay, and the labels are frigid, cold, cool, warm, or hot. Hot. Okay, let's say in Chennai. Okay, this is my longitude and this is my latitude, and based on these two features I have the label as cool. Okay, with me. Then there is Madurai and then there is Frankfurt in Germany, each having longitude and latitude, These are numerical values, and you also have the labels associated with it. Okay. So based on these three data points, how to classify, let's say, Velu with this latitude, longitude, and latitude. What do you think the weather might be? Okay. You only look at these three data points and classify the weather in Velu. Any answers? So you can calculate this distance. Okay. All of you can try this exercise. You can calculate the distance. So here it should be 7.27 minus 3.42 square plus 43.72 minus 43.53 square. You sum it up and take the square root. That's what your distance will be. And let me know what the label will be. Okay. Whichever has the least distance will be having, they'll be sharing the same labels. You can calculate it and let me know in the chat what will be the label here. And I want the distance metric also. And this distance you are measuring here is called the Euclidean distance. You can use some other distance metrics also, but for simplicity, you are going with Euclidean distance. This should be an easy calculation. You can do it in. You can use and calculate use a calculator also. Okay. I'm not doing any calculations. Just by looking at it, I can say these two, this point might be closer to Madurai. So I predict the climate or whether they'll be warm. Okay. This is how KNN works in general. Here you only have two features, but in actual real life data set, you might have hundreds or even thousands of features. Okay. And in summary, okay, you have these data points. Okay. You have same. I'm plotting these two here. Okay. Along with the class labels, class A and class B. Okay, this will become my training data set. And then one more new example comes into picture, Velu. Okay. I'm putting, it has this value. Okay. I'm putting it here. I calculate distance between all my neighboring points. And the number of neighboring points you have to take into account, that is what your K defines. Okay. You calculate distance. You have all these six distances between all these points. Okay. And let's say you decide your K should be 3. Okay. Then I'll take into account only the three closest points. Okay. Here in this circle. Okay? And I do something called voting. Okay. Here, voting based on what do you think the class will be? I have two in class A, two in class B, one in class A. So, what should be the class of this point? This question mark based on majority. I have two for class B. I have one for class A. What should be my prediction? Should it be class A or should it be class B? Mm, is everything that I told till now clear? I can explain it again if it's not clear. Okay, so based on majority voting, my answer should be class B. Okay, and if K is equal to 1, again my answer should be class B because this is my closest. I'll only look at this point. If K is 5, I take the 5 closest points here. Maybe if I take 5 closest, then my answer will change to class A. Okay, I'll include all these points. So again, your performance depends on the value of K that you decide. Okay, and in KNN, there is no hidden complicated math involved except for the distance metric that you define. Okay, but this is a simple two-dimensional case. You only have two features. But when you think of hundreds or even thousands, calculating that distance matrix becomes costly. It's not efficient. Okay, that's why when you have huge data sets, people actually don't prefer KNN. And this is one of the essential classification algorithms or in traditional ML that you can all try out and use. There's also a coding notebook after this. So any questions till now, any doubts, or can I move on to the next one? Hello, am I still audible? Okay, let me move on to the next algorithm, that is logistic regression. Okay, again, logistic regression is another popular machine learning method which is used for say supervised learning. It can be used for classification as well as regression. For the regression case, your output should lie between 0 and 1. Okay? But most of the cases, you only use it for binary classification. And what we do here is predict the categorical dependent variable. Categorical dependent variable means, as I explained before, whether the email is spam or not spam, you have heart disease or not. Those will be a categorical dependent variable. Again, continuous dependent variable. Again, I can think of only height here. Okay? With the help of independent variables. See, the output only should be categorical. Input independent variables can both be continuous and also be discrete. Okay. Let's say in this case here, see, these are all continuous variables and female, doctor, those are your categorical variables. Okay. You only have a uh, fixed number of professions you have. Okay, you have fixed number of genders. Those will be your categorical variables. But again, income is continuous. Okay, you can have it in any range. And the output of logistic regression, the value is between 0 and 1. Basically, what you do here is you model something called the probability, okay, of both the classes 0 and 1. Okay. Again, another use case is the credit card fraud detection case. You have your features and you have your labels. Ultimately, logistic regression is some sort of modification of linear regression. You have the sigmoid activation at the end. Linear regression, the output can have values in any range, minus infinity to infinity. But here in the logistic regression case, it's only between 0 and 1. That's because of this sigmoid activation that you use. The output variables can either be 0 or 1. So we should restrict the output of logistic regression also to be between 0 and 1. Okay. And this is the sigmoid activation here. Okay. And so this green line that you can see here. Okay. Any value, any input value you give lies on this line, this green line. Okay. That's why its range is 0 or 1. It's the value is between 0 and 1. Okay. So any, let's say you can calculate it for, x is equal to 10. It might lie somewhere in this line. And what we do is you take a cutoff, let's say 0.5. Okay. If your output is greater than or equal to zero point 0.5, you might say you have heart disease for sure. Okay. If it's below zero point 0.5, you can classify it as you don't have heart disease. Okay. And yeah, you define a specific threshold or cutoff. I've taken it as zero point 0.5 here, and then do the prediction accordingly. Remember the difference, linear regression, it need not be between 0 and 1, the values. Okay. You have the sigmoid activation at the end. After getting this x value from linear regression, you are using the sigmoid activation and making sure you restrict it between 0 and 1 because your categorical variable has values either 0 or 1. Okay. And you get the value of zero point 0.5 if your x or output from linear regression is 0. Okay. Any doubts in logistic regression? I think here there is a lot of math involved more than KNN. But if you understood linear regression, logistic regression is also, I think it would be a little bit easier to understand. Any doubts, questions? Can I go ahead to the next topic? Okay. So right now you have uh, an idea about KNN and logistic regression. How do you think I can compare or evaluate them to make sure that this for this particular data set, this algorithm works best for me? How do you evaluate these models? Okay. Any metrics you can think of? I think yesterday for a regression case, what all metrics did we use? If if you have gone through the notebook that I shared yesterday, you might have come across some metrics. There were all these formulas. One is coefficient of determination, R square. The uh, Then there's this Pearson correlation coefficient, then mean squared error, root mean squared error. Okay, those are all metrics that you can use for a regression case. For a classification case, you have something called the F1 score, you have accuracy. I think accuracy is a term most of you might have heard. This model is more accurate than this model. Then there is ROC, AUC, the receiver operator characteristics curve. Then there is precision and recall. These are all what you call evaluation metrics. Okay. And based on these evaluation metrics, you can actually select which model works best for this particular data set. You have metrics for regression here, for classification. You have metrics for unsupervised models also. And maybe in specific domains, let's say for images or text, you have the blue score is for text and so on. Okay. These are how you evaluate, these are different metrics. Okay. And I'll be showing in code, how do you implement these metrics. Mm. So first one that you can um, first one we can look at is called the confusion matrix. Okay. So actual, actual means actual labels that I already have. Okay. Uh, so these are my labels, actual labels that I have. Okay. And predicted is the one you get as output from your model. Okay. If your predicted value comes under the negative class and the actual value is also of the negative class, you get the, so it's actually a true negative. If both are positive, you get true positives. And if your predicted class is positive and the actual class is negative, it's actually a false positive given by the model. Okay. Again, the opposite case, you get false negatives. If you want a perfect model, okay, what should be the criteria here in the confusion matrix? Where do you want to see zeros? The model is perfect, 100% accurate. What all things you want to ideally reduce here? Reduce the number among these four. Okay, okay, maybe I can explain it with an example. Let's say you went to a center, let's say for medical center for COVID testing. Okay, you actually don't have COVID, that's your negative, but then the result comes as positive. Do you want that case? Do you want that to happen? Or do you want it to be negative also? The result should also be negative, the testing result. Just simple yes or no. Do you want a false positive result? If it's false positive, again, they'll ask you to isolate, don't go anywhere, stay in your room and stuff. Do you want that to happen? No, right? If you actually don't have COVID, the result should also come as negative. Okay, you don't want false positives to happen. But then again, in another case, you actually have COVID and the test comes as negative. Okay? You'll be freely roaming around again, spreading COVID to other people. You also don't want that case to happen. Okay, so you want to try to reduce type 1 error and type 2 error. Okay, that's how you make sure that your model is actually good. Here, ideally, here there should be zero false positives and zero false negatives. This is the confusion matrix case. Then moving on to precision and recurve. These are other metrics. Okay, precision, we can see it as a measure of quality. So here, precision is the you calculate it based on number of true positives divided by both true positives and false positives. Okay, and recall is a measure of quantity. So here in precision, you check how many retrieved items are actually relevant. Okay? And recall means whatever relevant items that I have, how many, whatever items are retrieved, how many of those are relevant. Okay. Maybe if I come up with an example, I can explain it better here. Maybe I'll explain it during the coding session, what precision and recall is. Then there is this ROC curve, okay, and AUC is area under the curve. Okay, a perfect classifier should have ROC AUC value as 1. Okay, uh, so a random classifier. Okay, you randomly make a guess based on the previous examples. You don't even look at let's say for the email spam classification case, you don't even look at the email. You keep making random guesses. Okay, that's what your random classifier is. In that case, you will have ROC AUC value as 0.5. Okay, if you as it keeps getting better and better and better, you keep trying different models. You try to make it better. It will slowly approach to 1 if you have the perfect classifier in hand. Okay, anything below this is worse. Okay, and yeah, this is your ROC AUC curve. And one more important thing to keep in mind is yesterday I was just talking about train and test splitting. Okay, how do you split the data into train and test? Okay, there are other, but again, the problem with just splitting it into train and test is, uh, let's say in your data set, going back to email classification again, you have, uh, let's say, out of 100 emails, I would say 90 of them are perfectly fine. 10 are spam emails. Okay. When you split the data set, there might be a chance that in your test set, everything might have, only the uh, relevant emails, not the spam ones. And if you apply You do all the training and you go on for evaluation, you see that the model is able to perfectly predict whether the email is spam or not. You get what I'm saying, right? So this is again something called class imbalance. You have more of the relevant class and less of the spam class. Okay. So this is one of the drawbacks of just splitting it into train and test. So there are other strategies. One is called cross validation, where you make sure you have the data set. Okay. You split it into different chunks, smaller parts. Okay. And this percentage split you can decide. So here you, let's say out of uh, seven different parts, you assign six to training, one alone you keep for testing. Okay. And you keep repeating this. I'll keep the first six here for training, the last one for testing. Then maybe the first one for testing, then the last six for training. I'll keep on repeating it until each of the data set chunk becomes part of testing. Okay. So here for each run, you get a metric value. You do an average across the uh, folds. We term these as folds. Okay. Do the average, and then you can actually arrive at a proper guess that this is actually my model performance. It's here in this case, your model might be over optimistic, but here in this case, you make sure that you can get the actual performance instead of the over optimistic performance. Okay. And then there is again non-stratified k-fold, then there is bootstrap. So these are different kinds of how you split the data and do the evaluation part. Uh, I think this might be a bit too much. I hope you all understood the cross validation and evaluation part. If you still have any doubts, I can repeat it. Any doubts? Yeah. So we looked at two classification algorithms. One is K and then the other one is logistic regression. We looked at how to do evaluation for different models. That is the cross validation here. Okay. And we also looked at different metrics for evaluation for just specific for the classification case. Okay, accuracy, F1 score, and everything. Okay. And yeah. So how many of you try the notebook that I shared yesterday for linear regression? Was anyone able to fill the variables and at least generate some plots, or was any of you facing any difficulties in running the code? I think you can raise your hand if you have tried it or not. The notebook that I shared yesterday. If no one tried it, you can you can say no also. That's fine. Anyway, I'll be showing the answers, and or was the code difficult to understand? Hello, am I audible? I'll start with the coding session. Yes. Is my screen visible? The coding part. Okay, good. Okay, so I'll start by. So this was for yesterday's linear regression. Okay, I filled in everything, and I'll show you how it works. Packages. I'll be importing NumPy, Matplotlib, Pandas, and we'll be mostly using the scikit-learn package to implement all these machine learning algorithms. Okay, so I have my linear regression class here, the ridge regression class, and the lasso regression class. And again, to split my data, I use the train test split function. Okay. To implement polynomial regression, I'll be importing the polynomial features class. I hope you all remember what ridge regression is, lasso is, and polynomial regression is from yesterday's class. And then the make pipeline function so that you can chain different operations together. Okay, I'll import this. Okay, and scikit-learn already has this diabetes data set. Okay, okay. So these are my features. Okay, I have my age, BMI, blood pressure, and these might be different measurements of taken from your blood. Okay, and this is my Y. These are my labels. What I want to do here is using all these features. Okay, I want to predict this value. Okay, this is the regression case. For these features, 151 is my value. Okay, it's as simple as that. Okay, but I will start with the univariate regression case. Okay, instead of taking all of these into account, I will start with a single feature, that is BMI, body mass index. Okay, I will assign it to X. I have my Y as this one. Okay, run it. Then I'll use, the matplotlib package and get a scatter plot. Did you all learn about matplotlib in the data visualization class? How to do scatter plots and everything? Matplotlib. Okay. Okay. Good. So I'll get a scatter plot to visualize how the relationship is. Okay. This is how it is. This is my X, this is my Y. Do you all think there is some kind of linear relationship? Can I fit a straight line through this or not? What do you think might be the best fit here? I can draw a straight line like this. I can draw it like this, like this. Okay. I think this might be, there is some kind of linear relationship, right? As BMI keeps increasing, my disease progression also increases. Okay. There is some, so it's not exactly linear, but there is some sort of linear relationship. Okay. So to so I was talking about two parameters, beta naught and beta 1 yesterday. Okay. How do I calculate it? Okay. This is my formula. Okay. This is my beta 1. This is my beta naught. Okay. So SXY means sum of squares of products of X and Y. Okay. You subtract the mean from both your Y and X, multiply it, sum it, that will be your SXY. SYY, you subtract Y from the mean, square it, take sum over all data points. Okay. And you get the slope as this. This will be my slope, and this will be my intercept. Okay. You don't need to worry about all these, formulations. Scikit-learn actually has a class that does this easily for you. You don't need to remember all these formulas. This is just I'm just showing it for how to apply all your linear algebra and NumPy stuff here. Okay, and I have these functions. Okay, so y is equal to, this is mx plus c. So this will be beta 1x plus beta naught, like I showed in the lecture yesterday. Okay, and you don't need to worry about these functions. These are for plotting. Okay, let's run this. So yeah, these are my labels. Okay, for 151, it should be 151, but it actually predicted 210. Okay, the error is also quite high. If I plot the predictions, so here are my labels, here are my predictions. If I get a perfect model, Okay, if there is a perfectly linear relationship, I shouldn't be seeing any points here. Okay, all of the points should lie on this straight line. Okay, but that is not the case since there is not that perfectly linear relationship between BMI and disease progression. If I take in some other feature, maybe it might have. I'll take blood pressure. Okay, this is I think yeah, we'll try this. See, again the plot is getting more scattered. That means BMI might be a better feature than blood pressure. Okay, this is one of the things. Instead of just visualization, we can use evaluation metrics. First one is coefficient of determination. You have the mean absolute error. You have the mean squared error, root mean squared error. Again, you don't need to worry about all these formulas. You have to make sure that these three are low and this is high. Okay, for your, for you to get a better model. Again, I've implemented these formulas here. You can try it out, and yeah, if you find these difficult, again, scikit-learn has convenient functions that you can use. Okay, see, this is it. My coefficient of determination is point around 0.2, mean average error, mean squared error, and root mean squared error. Okay, these are all quite high. You want your error to be as low as possible. Should be zero, ideally. Okay? Here, I only used a single feature, right? What if I take into account all the features? Okay, that's what I'm doing here. Do here. Again, you don't need to worry about this formula here. Let's see how it actually is. See, if I take into account all the features here, if I take in a single feature, it's 0.2 and the error is 4,000. It's around 4,000. But if I combine all, see, the error has reduced. My R squared, the coefficient of determination, has actually increased. So what you can learn from here is if you keep adding more and more relevant features, maybe that might actually help in better prediction. Okay. Yeah. If you don't want to, implement all these mathematical formulas and everything, that's where we use scikit-learn. You just use this class. Okay. You have your X and Y, use this. You do something called fitting the model. You train the model. You do that here. It's done. You get the coefficient of determination. See, it's the same. I got 5177 here, 5177 here. So what actually is happening in the back end is these things, these two. You don't need to implement this. Scikit-learn package already has this class. Okay, you don't need to do anything. Just define this model, do fit, do score. That's it. Okay. And these are my coefficients, model coefficients. This is my intercept. And if you want to get predictions for newer data points, you use model.predict. That's it. These are my predictions. And if you don't want to implement those metrics manually, you have your R2 score, you have your mean absolute error, you have your mean squared error. These are all functions you implement. You get it from scikit-learn. Okay. And yeah, can we make this better? We have used linear regression. Can we do better? There might be non-linear relationship. We can try to use polynomial regression. Okay. Again, here I'm taking a single feature. Okay, BMI. Okay. I'm doing the train test split here. Remember, we always have to split the data into train and test. Use training data for training and then do your test evaluation on test data. I'm using polynomial regression of different degrees starting from 1. What does degree 1 correspond to? What's its equivalent? Can anyone tell me? If my degree is 1, what does it correspond to? I showed it in the slides yesterday. Okay, that corresponds to your simple linear regression case. Okay, and yeah, make pipeline is what it tells us get different polynomial features of different degree and then do linear regression. Okay, I fit, I predict, get my scores appended to different lists because I want to see how does the degree of the polynomial affects my downstream task. Okay, I'll plot it. Let's see. See, this is your bias variance trade-off. As model flexibility keeps increasing, you see the train error keeps on decreasing. But then at one point, you see the test error jumps up till here. Okay? So based on this plot, what should be my ideal model flexibility? So say a number from 1 to 9. What should be my ideal degree here? When I was talking about bias variance trade-offs yesterday, I showed a point where there would be ideal model flexibility. What is that? What does that correspond to here? What should be my objective here? Okay. I want the test error to be as low as possible. And I think degree 6 here gives me the lowest possible test error. Okay. Is that clear? Here will be your underfit case. Here it will be your overfitting case. Okay. Then moving on to regularization. Okay. Here I'm using a random data set. Okay. I think NumPy you would have learned about this random module where I'm generating random samples. Okay. Again, I'm doing train test split. Okay. I'm intentionally making a model that overfits. So if my degree here is 30, okay, my model will actually overfit. And here I do use regularization. I'm using the ridge regression. Okay. Uh, Maybe it should be 30. I'm combining ridge regression. Okay. So ridge, as I told you before, it acts as some form of regularization. Okay. I get my predictions I from both my test and train case, calculate mean squared error, and I'm going to plot it. You see my overfit model. So blue represents my training data. As you can see, the green line, it follows the blue points more closely. See, that is your overfit case. But then if you apply regularization using the ridge regression method, you see the purple line, that's the regularized model. It does not follow the training data points. It also follows, somewhat close to the test data points also. You want this model to be able to, generalize with. It shouldn't only look at training data, and it shouldn't to, overfit to training data. Okay. And as you can see, if you do overfitting, my error is 1.64. See my test error. Okay. If I do some form of regularization, the test error actually reduces. Okay. And this is how you do regularization. You can switch ridge to lasso. I can also check. Okay. See, if I use lasso regression, my test error comes to 1.4. This is how you try different models and see which one actually works better. Okay. So here the regularized model is almost perfect. You want this type of curve. You don't want the green line type of curve here. Okay. I think, yeah. Any doubts? So there are three main steps. You get your data, define a model, do fit, do predict, get your score. That's it. ML is done here for linear regression at least. See the magnitude of difference between the overfit model test error and regularized model test error. Any doubts? Okay. Okay. Cool. Then maybe we'll move on to KNN and logistic regression. Okay. So here again, I use scikit-learn and NumPy module. I have imported matplotlib. First thing I'll do is generate a binary classification data set. Again, you have the make classification function from scikit-learn. Okay. I'm generating 1,000 samples, each having two features and one label. Okay. I split into training and test here. And then I'm visualizing how my data looks like. Okay. You see, this is my class 0, this is my class 1. This is how my data looks like. Okay. And if I plot a single test point, here is my test point, you know, this green cross mark. Based on KNN algorithm, if I choose K as 1, what class should I assign this point to? Should be very easy to say just by looking at it. What should be the class for this point? Should it be class 0 or class 1? I'm just asking for this specific point. So K, and then you look at neighboring points, you do some kind of voting. You don't need to do all that. For K is equal to 1, you just look at the neighboring point, the closest point. What should be the class? Should be class 0, no? Because it's surrounded by all these red points. It should be class 0. Okay. Then I'll try for different K values. Okay. I'll be looking at one neighbor, I'll be looking at two, three, all the way up to 10. Okay. And I'll get the accuracy score. See, for regression, it was mean squared error. Here I'm looking at accuracy score. Okay. See, I keep on increasing number of K. Okay. I want the error to be as low as possible. I can either pick three or eight. I think three would be the best. You don't need to look at more neighbors if you are satisfied with three itself. Three, and the optimal number of neighbors is also three. You want the error to be as low as possible. Okay. And see, I'm getting the score only for test case. Predicting, I'm fitting using train, getting the score using test. Okay. This is how KNN works. Here, n neighbors is something you have to define. Okay. You iterate through different K values, plot this curve, and choose the one that has the lowest misclassification error. Misclassification error is just 1 minus your accuracy. That's it. And you want that to be as low as possible. Okay. Again, moving on to logistic regression. Okay. I define the model here. Do fit, make predictions for test, get the accuracy score for test set. I'll be printing the score, and I'll plot something called the decision boundary. You see? So linear regression, you get this sort of line here. Okay. Anything that falls below this line, okay, below this line, you term it as class 0. Okay. Anything above this line, you term it as class 1. Okay. So is this model perfect? It's saying anything below this line is red, anything above this line is blue. That is what your decision boundary. So this is the decision boundary. So will you be satisfied with this model? Accuracy is quite good. It's not 1, it's not 100%. But yeah, see, if you see in this figure itself, even though there are a lot of blue points here, these are all misclassified points. Okay, so the model is not perfect. And if you want to do a comparison between these two, you go calculate the confusion matrix. You define the model, do fit, do predict. Define the model, logistic regression model here, do fit, do predict. Get confusion matrix. Confusion matrix, you pass in the original labels and the predicted labels. Okay, I will see. This is my KNN confusion matrix. This is my logistic regression confusion matrix. Based on the confusion matrix, which do you think is better? So true negative, false positive, false negative, true positive. Same here. So as I explained in the lecture, what should an ideal model have? Okay. So I think KNN is the better model since it has lower number of false positives and false negatives. Okay. And you can get your precision and recall score gain using functions from scikit-learn. Okay. This is my precision and recall. Okay. And if you want to get the ROC curve, this is the code that you have. You have the ROC curve function. You calculate the area under the curve. And yeah. So both of these curves have same area under the curve, that's 0.95. But if you so you have to take a decision here. You want to have a model with higher precision or higher recall, and yeah, you have to make a decision according to your case. So I think KNN would be the best since it has higher true positive rate, even though they have same area under the curve. Yeah. Any doubts? And I will just share this link here. This has access to, you can get access to all the slides and notebooks. You can execute it and see. You can play around with different number of Ks, or yeah, you can play around with different parameters and see how it changes. Any doubts? And it would be helpful if you could all fill this feedback form also. I'll include a separate section where you can post your doubts, okay, so that I can give an answer in the next class. If you don't have any questions or doubts, I think we can end the meeting here. Thank you everyone for attending.